Hello everyone, welcome to Abhi online classes. Today we will discuss some more problems in the chapter differentiability. Examine the continuity and differentiability of the function f of x is equal to mod of x minus 1 plus mod of x minus 2 at x is equal to 1 and x is equal to 2. We have to check whether this function is continuous at x equal to 1 and at x equal to 2, as well as whether it is differentiable at x equal to 1 and x is equal to 2. First we prepare this function. We use the definitions of modulus. Modulus of x minus 1 is equal to x minus 1 when x is greater than 1, and this is equal to 1 minus x when x is less than 1, and it is equal to 0 if x is equal to 0. Mod of x minus 2. Mod of x minus 2 equal to x minus 2 if x is greater than 2, and it is equal to 2 minus x if x is less than 2, and it is equal to 0 if x is equal to 2. Here x is equal to 1. So like this, mod of x minus 1 equal to x minus 1 when x is greater than 1. Mod of x minus 2 equal to x minus 2 when x is greater than 2. Mod of x minus 1 equal to 1 minus x when x is less than 1. And mod of x minus 2 equal to 2 minus x if x is less than 2. And mod of x minus 1 equal to 0 if x is equal to 1. And it is equal to mod of x minus 2 is equal to 0 if x is equal to 2. Now we prepare the function. This is 1 and this is 2. These are all greater than 2. All these x's are greater than 2. That means it is 2 plus, and this is 2 minus. In the similar way, all these x's are greater than 1. That is, they are all in the positive neighborhood of 1. All these x's are less than 1. They are in the negative neighborhood of 1. We split mod x minus 1 as x minus 1 when x is greater than 1, and mod of x minus 1 is equal to 1 minus x when x is less than 1. And also mod of x minus 2 equal to x minus 2 when x is in the positive neighborhood of 2, and 2 minus x when x is in the negative neighborhood of 2. That means this is splitting like this, and this is splitting like this. Okay, first we prepare f of x when x is greater than 2. When x is greater than 2, f of x is x minus 2. From mod of x minus 2 we got x minus 2. When x's are greater than 2, they are all greater than 1. Mod of x minus 1 is x minus 1. So mod of x minus 1 is x minus 1. Mod of x minus 2 is x minus 2. That is, we are getting 2x minus 3 when x is greater than 2. When x is lying in between 1 and 2, when x is lying in between 1 and 2, we have mod of x minus 1 equal to x minus 1. Mod of x minus 2 as 2 minus x. X minus 1 plus 2 minus x. Cancel x. 2 minus 1, 1. F of x is becoming 1. So, next, when x is less than 1, we prepare. When x's are less than 1, mod of x minus 1 is equal to 1 minus x plus, in between there is plus, so plus. When x's are less than 1, these are all less than 2. All these x's are also less than 2. When x's are all less than 2, we should write mod of x minus 2 as 2 minus x. So we got 1 plus 2, 3. Minus x gives minus 2x. So we have prepared 3 functions. When x is greater than 2, f of x is 2x minus 3. When x is lying in between 1 and 2, f of x is 1. When x is less than 1, f of x is 3 minus 2x. So we got f of x like this. X is greater than 2 means x is in the positive neighborhood of 2. That means 2 plus. X is less than 1 means x is in the negative neighborhood of 1. That is 1 minus. Here we have 4 options. X is equal to 1. X is greater than 1. X is equal to 2. X is less than 2. That means it is in the negative neighborhood of 2. It is 2 minus. It is x is greater than 1. That is in positive neighborhood of 1. So we prepared f of x like this. First we check whether this function is continuous at x is equal to 1 and derivable at x is equal to 1. First we see at x is equal to 1. It is continuous and derivable or not. First, continuity. We check the continuity at x is equal to 1. First, left-handed limit. That means limit x tends to 1 minus. We are going to check continuity at x is equal to 1. So, 1 minus f of x. Limit x tends to 1 minus. Where it is 1 minus. F of x is 3 minus 2x. We convert into h. Limit h tends to 0. 3 minus 2 into, we replace x by 1 minus h. Put h equal to 0. 3 minus 2 into 1 minus 0. That means 3 minus 2, 1. So we got left-handed limit 1. Now we see right-handed limit. Limit x tends to 1 plus f of x. Limit x tends to 1 plus here. Therefore f of x is 1. Limit of constant is constant. Next we see third one, f of 1 equal to 1 also here. Put x is equal to 1 here. Put x is equal to 1. F of 1 equal to 1. Therefore, conclusion is left-handed limit equal to right-handed limit equal to f of 1. All the three results 1. All these results are equal to 1. So, therefore, 3 are equal. Therefore, f is continuous at x is equal to 1. Now we see differentiability at x is equal to 1. First, left-handed derivative. Limit x tends to 1 minus f of x minus f of 1 by x minus 1. Limit x tends to 1 minus. Here f of x is 3 minus 2x minus f of 1 is 1 itself by x minus 1. Limit x tends to 1 minus 3 minus 1 gives 2 minus 2x by x minus 1. Limit x tends to 1 minus, we take 2 as common. Cancel x minus 1, this is minus 1 times. So limit of constant, that is minus 2, 2 into minus 1 is minus 2. Limit of constant is constant. So we got left-handed derivative of f at 2 at x is equal to 1 is minus 2. Now right-handed derivative. Limit x tends to 1 plus f of x minus f of 1 by x minus. Right-handed derivative. Limit x tends to 1 plus f of x minus f of 1 by x minus 1. Limit x tends to 1 plus. 1 plus I will show in another paper I have written. When x is in 1 plus, f of x is 1. At x is equal to 1, f of x is also 1 by x minus 1. Cancel plus 1 and minus 1. We got right-handed derivative 0 by something 0. Therefore, left-handed derivative of f at 1, right-handed derivative of f at 1, both are not equal. Left-handed derivative is minus 2 and right-handed derivative is 0. Therefore, they are not equal. Therefore, f is not derivable. Yet, x is equal to 1. So, this is the given function is continuous at x is equal to 1, but this is not derivable at x is equal to 1. Now, we check continuity and derivability at x is equal to 2. First, continuity. Left-handed limit of f at 2. Limit x tends to 2 minus f of x. Limit x tends to 2 minus. When x is 2 minus, when x is in negative neighborhood of 2, f of x is 1. Therefore, limit of constant is constant. Now we'll see right-handed limit. Limit x tends to 2 plus f of x. When x is in positive neighborhood of 2, f of x is 2x minus 3. Limit x tends to 2 plus. When x is in 2 plus, f of x is 2x minus 3. We replace f of x by 2x minus 3. Limit h tends to 0. 2 into, we replace x by 2 plus h minus 3. Limit h tends to 0. 4 plus 2h minus 3. 2 into 2, 4. 4 plus 2h minus 3. Limit h tends to 0. 4 minus 1. 4 minus 3. 1 plus 2h. Put h is equal to 0. 1 plus 0 is equal to 1. So we got right-handed limit 1. Left-handed limit is 1 and as well as right-handed limit is also 1. Now we will see f of 2. At x is equal to 2, f of x is 1. Therefore, this is also 1. Therefore, conclusion here is left-handed limit of f at x is equal to 2. Right-handed limit of f at x is equal to 2 and f of 2, these three are equal. 3 are equal to 1, 1, 1. Therefore, f is continuous. Yet, x is equal to 2. Now, differentiability at x is equal to 2. At x is equal to 2, we check whether it is differentiable or not. First we see left-handed derivative of f at x is equal to 2. Limit x tends to 2 minus f of x minus f of 2 by x minus 2. Limit x tends to 2 minus, we are in the negative neighborhood of 2. When x is in 2 minus, f of x is 1. F of 2 we want. When x is equal to 2, f of x is 1. F of 2 is 1 by x minus 2. I repeat, when x is in 2 minus, f of x is, when x is in 2 minus, f of x is 1. F of 2, when x is equal to 2, f of x is 1. For both f values, both are 1. So 1 minus 1, 0. 0 by something, 0. So we got left-handed derivative 0. Now we'll see right-handed derivative of f at 2. Limit x tends to 2 plus f of x minus f of 2 by x minus 2. Limit x tends to 2 plus. When x is in 2 plus, and this is f of x is 2x minus 3. Minus, when x is equal to 2, put x is equal to 2 here. F of 2 is 1 by x minus 2. Limit x tends to 2 plus. 2x minus 3 minus 1 minus 4 by x minus 2. Limit x tends to 2 plus, we take 2 common, by x minus 2. Cancel. Limit of constant is constant. So we got right-handed derivative of f at x is equal to 2 is 2. Left-handed derivative of f at 2 is 0. Therefore, left-handed derivative is not equal to right-handed derivative. Therefore, f is not derivable yet x is equal to 2. This same function is continuous at x is equal to 2. Similarly, we have shown derivability also here. F is not derivable at x is equal to 2. Continuous but not derivable. At x equal to 1 also this is continuous and not derivable. At x equal to 1 also we have seen. Therefore, f is continuous at x is equal to 1 and 2. F is not derivable at x is equal to 1 and 2. Till now we have seen how to answer this question in descriptive way. Suppose if it is asked in objective type, I want to give you a small note. If f of x is equal to mod of x minus alpha plus mod of x minus beta, then definitely this function is continuous at x equal to alpha and beta. But this is not differentiable, not derivable at x equal to alpha and beta. That is the main important note. For objective type, this note will be helpful for you. Now we will discuss one more question. Examine the differentiability of the function f of x equal to x into tan inverse of 1 by x when x is not equal to 0 and f of x equal to 0 when x is equal to 0. Now we check whether this function is differentiable or not at x is equal to 0. Obviously this function is continuous. We have seen in the chapter continuity. I will provide the links in the description box so you can go through the links and check the continuity whether this is continuous or not. Obviously this is a continuous function. Now we check differentiable or not. First we see left-handed derivative. Left-handed derivative of f at 0 we have to see. Limit x tends to 0 minus f of x minus f of 0 by x minus 0. Limit x tends to 0 minus, that means it is not equal to 0. When x is in the negative neighborhood of 0, that means it is not equal to 0. We write f of x as x into tan inverse of 1 by x minus, put x equal to 0 here, f of 0 is 0 by x minus 0, that is x. Limit, I write here, limit x tends to 0 minus x into tan inverse of 1 by x by x, cancel x. Replace limit h tends to 0, replace x by 0 minus h, tan inverse of 1 by 0 minus h. Limit h tends to 0, tan inverse of minus 1 by h. We write this as minus tan inverse h minus. Limit h tends to 0, tan inverse of 1 by h. By substituting h equal to 0, we got minus tan inverse of 1 by 0. That means tan inverse of infinity. Tan inverse infinity is pi by 2, therefore it is minus pi by 2. So left-handed derivative, repeat. Limit x tends to 0 minus f of x minus f of 0 by x minus 0. Limit x tends to 0 minus, here f of x is x into tan inverse of 1 by x. By putting x is equal to 0 here, f of 0 is 0. By x minus 0 is x itself. So cancelling x, and we replace x by 0 minus h. Tan inverse of minus 1 by h we are writing as minus tan inverse of 1 by h. Put h is equal to 0. Tan inverse of 1 by 0 means tan inverse of infinity, that is pi by 2. So we got left-handed derivative minus pi by 2. Now right-handed derivative of f at 0. Limit extends to 0 plus f of x minus f of 0 by x minus 0. Limit extends to 0 plus, when x is in positive neighborhood of 0, that means not equal to 0, we write f of x as x into tan inverse of 1 by x. F of 0, putting x equal to 0 here, f of 0 is 0 by x minus 0. Limit extends to 0 plus x into tan inverse of 1 by x by x. By x. Cancel x. Limit h tends to 0. Tan inverse of 1 by, we write in place of x 0 plus h. So that means limit h tends to 0, tan inverse of 1 by h. Put h equal to 0 here. Tan inverse of 1 by 0. Tan inverse of infinity. By putting h equal to 0 here, tan inverse of 1 by 0. 1 by 0 is infinity. Tan inverse infinity, we got pi by 2. I repeat, right-handed derivative of f at 0. Limit extends to 0 plus f of x minus f of 0 by x minus 0. Limit extends to 0 plus, we write f of x as x into tan inverse of 1 by x. F of 0 is 0 by x minus 0. Limit extends to 0 plus x tan inverse of 1 by x, cancelling x, and we replaced x by 0 plus h. Tan inverse of 1 by h we got. By substituting h equal to 0, tan inverse of 1 by 0, that means infinity. Tan inverse of infinity is pi by 2. Previously we have seen left-handed derivative of f is minus pi by 2. Right-handed derivative of f at x equal to 0 is plus pi by 2. That means they are not equal. Therefore, left-handed derivative is not equal to right-handed derivative. Therefore, f is not derivable at x is equal to 0. Therefore, this function is continuous at x equal to 0, but this is not derivable at x is equal to 0. Hope you understood this class. Thank you.